We have here a particle having mass m, and on that particle are acting various forces. So let's say that the first force is this F1 in certain direction. Let's say the second force is F2 in another direction. Let's say that F3 acts in certain another direction, and so on and so forth. And due to these forces, let's say this object, which was initially at velocity v sub I, if its velocity was initially v sub I, we want to know what would be its final velocity. So let's say if it reached here, tracing a path like this that we really don't know anything about till now. If that object just reaches here, then we want to know what would be its final velocity. In other words, what would be v final in that case? So we will approach this using the work-kinetic energy theorem, and let's get started. So right away, what we notice is that these forces are doing some work. So that means that the work done by F1 plus the work done by F2 plus the work done by F3, they all get added up as this particle traces this path. So for the sake of simplicity, let's just assume that the sum of all of these forces that are acting on this particle, let that be equal to F external. And let F external be written as, since we only deal in 3 dimensions in physics, so we will just take F external to be equal to F sub x times I hat plus F sub y j hat plus F sub z k hat. And due to this, now what you can do is you can write an expression for the work done by this net external force. So given that it traces some certain path, which is given right here, what you can always write that the work done by this external force is equal to the integral of F external dot dr. And this is the dot product, since if you take a certain displacement, let's say this is the dr segment you're talking about, and on this dr is the net force external looks like this, then for this minuscule amount of displacement, the work done is dw, and that dw is this, and you're just integrating that. If it would have been a straight line, you could have just done the dot product right away. But this right here, what you can do is you can further write dr vector as dx I hat plus dy j hat plus dz k hat. And we don't know anything about the relationship between dx, dy, and dz, but we just say that we have written dr in that way. And since we already know what f of x was, f external is, what you can do is you can do the dot product. So in other words, this integral can be written as the integral of f, the first component here is f sub x times dx, so you multiply these I hat components, then you multiply the j hat components, and then you get f sub y times dy plus f sub y times dy, and the third one will be f sub z times dz, and it's in green, so let's just do that in green once again. And so the next part will be f sub z dz. And where are you integrating it from? So let's not put any values right now. Let's just say from I to f, from the initial condition to the final condition. What you can do now? So, well, let's just separate these 3 integrals into 3 separate individual integrals. So then what do we get? So the first blue one you will get, using the first blue one you will get from initial to final of f sub x dx, plus for the orange one, the y one, you get from initial to final of f sub y dy. For the third one, you get from initial to final of f sub z dz. What else can we do? So we do know by Newton's second law that f sub x, f sub y, and f sub z are since they are the components of the force, and the net force, that is the net force acting here, is actually equal to mass times the acceleration of that object. What you can do is you can write for each of these, for f of x, you can write that f of x is equal to the f of x net is equal to mass times a acceleration in the x component. For y you can do the same, for z you can do the same. So what will happen here is, for the first integral right here, you would write from initial to final of m times a sub x dx. For the second integral, you would write from initial to final of m sub y, from ma sub y times dy. And for the third integral, you would have from initial to final of ma sub z times z. Let's try to simplify it a bit more. So we have arrived at a condition where we can start working with this. So I want to remind you of an equation that we have talked about before, and that is if you have the acceleration of something, so the acceleration of something going on in a one-dimensional motion, that can be written as the time derivative of dv over dt, but you can also write it as dv over dx times dx over dt by the chain rule. And this dx over dt is nothing but v. So what that means is that since these three are separate one-dimension motions that we have here, you can write all these a's in terms of v and dv over dx. So let's do that. Let's write it in that way. So the first integral, instead of ax, you would write from initial to final, you have mass times, instead of ax, you will write v sub x times dv sub x over dx times dx. And if you see here, you can cancel these dx's out, and you would arrive at from initial to final of m times v sub x times dv sub x. Now m is constant, so you can just take it out of the integral, and you would arrive at m from initial to final of v sub x times dv sub x. And now that we have something that we're going to integrate on, we can change our initial and final conditions, and now we can write, instead of, since we are dealing in velocities, instead of initial, you can now write velocity initial in the x direction, and instead of final, you can write velocity final in the x direction. If you compute this integral is going to be, let me just make a bit more space for this. This integral, let's do that right here. This integral is going to be 1/2 of v sub x squared from v initial x to v final x. You just evaluate this times the mass. And while you're at it, you would just put it in, you would just put this in and then subtract the value that you get from putting in second time. So then you would get, for the x direction, this integral that we had here, that we started with here, that comes down to be equal to, since 1/2 is a constant, you can just write that outside. You would arrive at 1/2 times v sub x squared. While putting in the final one, you would get vfx squared, and then minus vix squared. This is the value of this integral that you had right here. If you do that same for the y component, if you do that, then you would just arrive at the same result, except for the fact that now instead of x's, you will just write y's. And similarly, you will do that for the z direction, since you're just dealing with one-dimensional motion when you're taking components. So in the end, that will reduce down to, for the x component, you'll have 1/2 vf sub x squared minus vix squared, plus for the I direction, now you would have 1/2 m times v sub f y squared minus v sub I y squared. And then for the z direction, same thing, just change the subscript. You would arrive at 1/2 m times v final in the z direction squared minus v initial in the z direction. And what you can see here is that 1/2 is all common, so you can just write it out. So 1/2 is now taken out. And then what you can do is you can group the final terms right here, the final velocities, and you can write that together. So that will be equal to v sub fx squared plus v sub fy squared plus v sub fz squared. That minus the initial part, that initial part is just, instead of f, you will write I. And then you would arrive at v sub I x squared plus v sub y squared plus v sub I z squared. And this right here, believe it or not, really outstandingly, this right here is nothing but the dot product of the v final with itself. So v final times v final is this product that you have right there, since v final is just equal to vfx time comma vfy time comma vfz. And similarly, this part right here is just the dot product of v sub I with itself, since, well, again, you know that. And now, really interesting, what you arrived at is that the thing you started with, the work done by all the forces that you have, that is equal to 1/2 m times vf, since vf dot vf is nothing, just vf squared, the square of the magnitude of this vector, that minus the initial part. And that's it. This right here is the foundation of work-kinetic energy theorem. So let's just go back to where we started. So we started here. We started with this particle right here. So that means that the work done by all of these forces, and let me just write it out again, it's really important. The work done by all of these forces, all these external forces, is equal to 1/2 m times v final squared minus v initial squared. And if you want to break it down a bit further, what you can do is you can write this separately as 1/2 m v final squared minus 1/2 m v initial squared. This right here is nothing but the final kinetic energy of this object. So final kinetic energy, and this right here is the initial kinetic energy of the object. The initial kinetic energy of the object. So for a single particle system, that's what we have proven for till now. For a single particle system, the work done by all of the external forces, the sum of all of that, that is equal to the difference in the kinetic energy of the object that you're taking into consideration. And this right here is the work-kinetic energy theorem. And from this, we can solve really complex problems in physics, not just something that comes up on a contest, but also real-life situations where you need to estimate things for things like a spaceship or a submarine or all sorts of cool things. That is the foundation for that. See you in the next video.